Everyone. Sorry, I was just setting myself up. Welcome back. Happy Monday here. I hope y'all had a restful break. Welcome, welcome. Let's go ahead and jump into our check-in so we could see who we're missing. All right, February 22nd. I think is like the last weekend in February. Okay, so this is an interesting one. It might be maybe hard, but let's see. What is something that you do that might bother other people? So try to think of something that you do. It could even be like a sibling or something, some like something you do that kind of like would bother other people. I already know what's mine. So mine is for surely if whenever I was in college, I had to sit kind of in the either way in the front with the teacher as long as there weren't other students there, or I would have to sit way in the back where there weren't a lot of chairs around me or there are empty chairs around me because I'm actually a leg shaker and that bothers a lot of people. A lot of people don't like that vibration of like of the moving of a leg. I don't know. I just tend to use up my energy like that. Okay, talk a lot. I don't know how to whisper, really. Oh my gosh, that's my sister. Same, LOL. Talk a lot or laugh loudly sometimes. Okay, yeah, those are valid. These are good ones. Try to come up with it. It's a little bit hard, but there are little things. I click my pen to focus. Yeah, I think that's actually something I might do too. Or I fidget a lot. Maybe I do a lot of movements. Okay. I talk a lot sometimes. That's all right. I participate a lot. You think that might bother others? I love the participation. Um, oh, getting up a lot to walk. I don't talk unless I know the person. Yeah, oh yeah. I know how like sometimes people get bothered if someone's not talking enough or someone's talking too much. There's always something, right? Um, yeah, these are great. Let me just see who we're missing. Again, feel free to put in your final thoughts if you're still thinking. And then y'all can help me round up who we're missing here and or correct me if I'm wrong. Okay, I see. I said the worst images I can find to my best friends. I think that's what they said. My laugh is not okay. I tend to be super loud. These are good. I'm not easily bothered by others, but I know that some stuff I do might be like, ugh, to other people. All right, so this is who I'm missing. Kaylin, James, Sophia Pena, and Grecia. Again, let me know if I'm wrong, if I accidentally missed you. Um, Otherwise, let's try to text these folks to get them to come on in. Again, that's Kaylin, James, Sophia Pena, and Grecia. Okay, other than that, thank you all so much for sharing. I hope you're ready to dig back into math. Yeah, we have about a week and a day left in this module. So I don't know if all your advisors have shown you that. It's basically this week and then Monday, and that's going to be the end of this module. And then next week you have presentations of learning, the mini presentations of learning, if you remember that. It was that week where we had like mandatory office hours for some students, and then in the afternoon it was presentations, the mini presentations of learning that didn't go over like 10 minutes or so. Think I forgot how long. I think it was like or maybe it was a 15-minute slot. All right, and then it's a good question. What days are my office hours again? So I have them Monday through no Tuesday, Wednesday, at 1. Nope, at 2. Tuesday, Wednesday at 2. I also did have small group for today too. If anyone wants to be invited to small group, that's at 10 tomorrow. Feel free to let me know, and I'll be happy to invite you to small group. Okay, y'all. We just had our attendance check and we're going to jump right on in. We're going to be talking about concavity today. So we're kind of like, remember we had our big ideas packet. I'm literally going to like down the big ideas packet so you kind of know what's next. The slides should be posted. So if you haven't yet, you want to make sure you go to Google Classroom and open up today's slides. I think it's day 7. Day 7 is today. And right after we talk about concavity, we're going to talk about the second derivative test. So we talked about the first derivative before you all went into break. We're going to take a look at what the second derivative test is, and then we'll have our checkout. I posted that asynchronous number 5 is posted. That one is due tomorrow, Tuesday. So let me show you first. Again, I'm also allowing you all time to open up your copy of your slides. So use this time to do that. Let me also go to Google Classroom. So that's going to load, and then you see asynchronous number 5 is right here. And our slides are down here. So again, our slides are day 7. I mean, I can move this up if everyone wants it at the top, but let me show you asynchronous number 5. So what asynchronous number 5 is you all reviewing the first derivative test, actually. What I have there is linked kind of like the resources. So you could look back at slides day 4. If you click there, it'll take you to it. Or you could look back at our big ideas packet. What I have for you is kind of like that same picture you had in that Desmos activity. And what I'd like you to do is kind of just in your own words, describe at least 5 steps of what's happening in this picture. And you could totally use the big ideas packet. I'm even asking what big ideas do you think we're applying? You'll enter it in the box. Lastly, given this sign chart in this example of a first derivative test, you're going to be asked to try your best to sketch the graph of the function. Why does it say parent function? Just of the function. It's not a parent function. And then I want you to try to label your graph with what you know that the sign chart gives you. So that's the homework tomorrow. So again, it's reviewing first derivative test. Oh yeah. Oh yeah. There we go. Here's my office hours, by the way. It's always going to be up on your homework. So again, Tuesday to Wednesday at 2. If anyone wants to drop by. Does anyone have any questions about the next asynchronous that's due? Again, it's reviewing first derivative test. It is due tomorrow. Okay, just making sure that you all know that there's some time for you to like in the asynchronous time for you to like stop and just review the stuff we did because it was a week ago. And I get that, it's been a while. So yeah, let me go ahead and X that out. I hope you all made your own copy of the slides though. Again, it's in our Google Classroom and we're on day 7 right here. So I'm gonna go back to our slides. Yay. And I'm gonna hit present. All right, so let's go ahead and jump into what we're doing today. Recap, y'all. So the first derivative test, your asynchronous assignment is to kind of review this on your own. And what I want to tell you is if you find yourself freaking out because you forgot a lot or something, then you want to jump into my office hours and I'm happy to walk us through and so forth. So that's just a thing. And our office hours are Tuesday, Wednesday at 2. Okay. All right, so then what was the first derivative test that we learned when we went off into break? So before that, so remember the first derivative tells you a lot of information actually about your OG function, your original function. It tells you when and whether the function is increasing or decreasing, or if it's constant, how steep it is sometimes. Mostly importantly, we've been using it to find local maximums and minimums though, using the sign chart. And remember, there was a whole process to it. You have to find something called critical numbers, if you remember. And you want to test those critical numbers using a sign chart to check whether you have local maxes or local mins. And again, there's different terminology. Some call them relative maxes, mins. There's different things. Remember the how. Most importantly, using the sign chart, you place your critical numbers on a sign chart and you divide your number line into kind of segmented intervals and you have to test each of those segments if you remember. And again, you use the following guidelines to check whether or not you have a maximum or minimum. So if the derivative, the first derivative, changes from positive to negative, then you have a maximum. So remember, positive to negative means the slope is increasing, and then the slope is positive, and then the slope is negative. Therefore, you'll have a max. So that's what the first derivative test is telling us. And alternatively, you have when the slope goes from negative or decreasing to positive or increasing, then you know you have a minimum. And usually we draw these, I draw this picture to kind of just visualize what this rule is telling me. So that was just kind of like a review of what we talked about last week. And then you all did some stuff in groups where you tried to kind of apply the first derivative test. Let me know if anyone has any questions. This is again a recap. This one's not the new stuff yet. Okay, great. That was recap. And I did put some tips down there in yellow, how to review this. So again, if you're like, hey, I forgot everything, you can look at your big ideas packet for the full steps, or go back to our slides. They're all posted and you can review that. Or you could also check out the Padlet that we've been working on as well, which is linked in the slides. And again, if you want to get more practice, come on into my office hours and I'm happy to help explain certain things. All right, as an example, this is a screenshot, I think, from slides day 4 that I took, just a reminder of the process. Remember, there were certain steps that I verbally typed out in purple about what we're doing when it came to the first derivative test and how we use a sign chart to determine whether or not we have increasing or decreasing intervals and whether or not we have maximum or minimum when we're testing around a critical point. Again, let me know or pause me if you want to ask anything about this recap, but this is just me recapping so that we're not completely just jumping in head first without a reminder of what we're doing. So again, that was just a screenshot from last time. And to remind you all that when we did that Desmos group work together, you all were practicing how to make, your sign charts, how to find critical numbers, so forth. So this was some of the works that y'all did. And from your sign chart, you all were able to try to create a sketch of the original function. Again, I've been calling this the OG function. And again, many of you were like, I understand we needed some more time. But ultimately, what you want to do is move from first or second derivative test into sketching a good representation of what your original graph looks like with what the sign chart is telling you. So that's just a little review on that. And then again, this, it's the same photo that you all analyze in your groups. Again, I'm bringing this back and letting you know that there's times when you may have more than just one critical point. In this particular example, you have 1, 2, 3 critical points. That shows up when you're solving for X. If you look up here, we had 3 different X solutions. And that's what led us to have 3 different critical points in this example. So in this particular example, we had 1 local maximum and 2 local minimums due to the sign chart and what we analyzed. And again, some of you were able to go ahead and kind of create that and find that for groups that made it there. But if you didn't make it, that's why I definitely added in to this asynchronous work. So you could continue to analyze this, continue to develop questions if you have them, and, bring them into office hours or text me and remind, and I'm happy to, explain too. Again, that's our recap. Feel free to pause, ask questions, or use the chat. And yeah, there's just a little reminder there. Again, you can have multiple critical points. It's nice when you just have one. Usually when you have one, it's kind of like a parabola kind of thing. But you can have multiple, but the steps would be the same steps. Sometimes though, if their function looks long, or like it kind of has a lot of terms, like this one, not a lot of terms. It has like a high exponential term, then you know you got to kind of factor. So sometimes factoring comes into the picture. And then remember, this is something we discussed that was could be an obstacle for some of us because it's like factoring. We kind of got to spend time on reviewing for that. But don't forget that in your big ideas packet, I linked up the tool where you could check your factoring. So that shouldn't be a hindrance. So that should be okay for us. But just be aware that, factoring can be involved. All right. So now this is the part where we're going to pause and reflect. For this one, we're not on Padlet. We're using the chat, actually. So you can send me a private chat, or you can send one to everyone. So pause and reflect. I just did a little bit of a recap of what we did before we went into break. Now, it's been a week. How do you intend to review and refresh yourself to best prepare yourself for the end of this module? Because again, we only have this week and a day. So how do you intend to review and refresh yourself? Take a moment and put your thoughts there into the chat. All right. I'm loving the ideas so far coming in. So I have a lot of direct messages. Don't worry, I won't read names. But these are all great ideas. So I want to share it with everyone. So I'll try to catch up on like learning what I have missed out on. Looking back at my annotated slides. I love that because see how those annotations, you could go back and take a look at the little notes you made on your slides on your own copy. This is another great, like I like the specific next steps. I intend to try out the asynchronous review notes, right? The one that's going to be due tomorrow. That's great. And if I don't understand, then follow in with office hours. I love that plan. What I'll do to review and refresh myself is by doing example problems and asking questions. Yeah, you could go back to the slides and where there's the examples, just try them on your own and you could check. Oh, I love that. Go over the slides and big ideas packet. So both of them, because those are both key resources. I will look over the parts that's stuck on and look at the available resources. Awesome. Review slides. Ooh, and Khan Academy. That one's added in there. That's a good one. And yes, if stuck, still attend office hours. I'm going to take my time and learn things step by step. Yeah. We got Khan Academy, practice examples. Go over things I can't answer or remember off the top of my head. Yes, I plan to look over all the work and make an effort to understand everything. Awesome. Also, we'll try to go to office hours. Yay, these are all great plans because you do want to set yourself a plan. And it might not just be for this class, it might be, for your other classes too. I think, some of us 3 classes, some of you have portfolio, some of you have the full on 3 course load with Zooms and all that. So just pause and reflect on that. Thank you so much for sharing. Yay. All right. This is awesome. And by the way, I'll look forward. I'll be in office hours waiting to see if anyone needs my support. So I'll look forward to if anyone needs me there. All right. Let's jump into our new stuff, right? So I just recapped. We talked about steps and refreshing. Now let's move on to the next thing. So again, you want to make sure you make your own copy of the slides and annotate so that you can, go back to questions that you had or go back to like rephrasings of your understanding. So this is called changing slopes, and I put AKA changing derivatives. So remember, slope and derivative, I kind of use it interchangeably. Because usually I draw slopes on a graph to kind of see how the derivative is behaving, and that's why I kind of use it interchangeably. Our learning target today, though, is I can connect. So now we're looking at the second derivative of a function to concavity. Now, don't worry if you don't know what concavity is. We're going to talk about it. So let me just pause here so y'all can read this. Remember, we don't have to write it down on a piece of paper. You're on your own copy of the notes, but feel free if you want to copy this down if you'd like. All right, y'all ready? Okay, so that's our learning target. Keep that in mind, and or you could, go back on the slide. Okay, so what is concavity? The best way I found to explain it is with a picture. So concave up, I kind of like to think of it like of a parabola that's facing upward, but these are different examples. So this is called concave up decreasing because if you were to like kind of like walk on this, imagine you're on a path and you're walking along this, you're kind of going down a hill if you're going from left to right. So it's, oops, it is decreasing, but it's facing upward, like it's kind of cusped upward, kind of like an upward facing parabola. So this is called concave up. This is on this side over here. This is concave up increasing. So it's like you would have to walk up a hill, and it's also cupped upward. Like the curve is kind of going like cupped upward. Then you have the examples of concave down, which are both down here. There's concave down decreasing. That means you're going to walk down a hill, or there's concave down increasing. You could walk up a hill. So take a look at that. Let's see if anyone has any questions about that. I know I explained that very generally. There is a formal definition though. Yeah, let me also put my office hours. So yeah, Tuesdays to Wednesday at 2 p.m. And I think our reserved one is the AP Calc specific reserve one is tomorrow, but you're also welcome to come in at Wednesday too. So I put in the office hours right there into the chat, or there's small group, which is at 10 tomorrow and 10 on Wednesday. But for small group, you want to send me a message. And then I'll be happy to jump in and support. Yeah. All right, so that's concavity. The best way, like I mentioned, I explained it with pictures. But let's talk about how this even connects to slopes or changing slopes anyway. That's in our next slide, so take a look. So concave upward, another way to describe that using slope is when the slope increases over time. So I really like this picture because as you can see, right here, this line, the first line, like if I was to draw a tangent line or, right here, you notice that the slope is less steep than if I were to draw the line up here. The slope is really steep. So the slope goes from less steep to really steep. When the slope is increasing, you have concave up or concave upward. Alternatively, concave downward is when your slope is decreasing over time or over as x gets larger. So basically, if I was to draw a tangent line right here on the curve, the slope would be very steep. But if I was to draw a tangent line up more on this curve, the slope gets less steep. Therefore, it goes from more steep to less steep, and the slope is decreasing. That would define this as concave downward. I do have another example of this on the next slide in case this doesn't do it justice. But let's see if anyone has questions about this so far. Concave up, concave down. This is the less general definition because originally I just said it cusps upward or cusps downward, but now you kind of have how it relates to slope definition coming in here. All right. Cool. So let's continue to kind of investigate what I mean about this change in slope when it comes to concavity. Oh, okay. Concavity relates to the rate of change of a function's derivative. Again, there's a lot of vocabulary word in that one sentence. So the rate of change of a function's derivative. or the rate of change of the slopes, or how the slopes are changing. So how do you connect this with the derivative though? So we just now make connections with concavity to slopes, but now let's make the relation of concavity to the derivative. So a function is concave up when the derivative is increasing over time. See how that's kind of interchangeable with slope? And alternatively, it's concave down when the derivative is decreasing over time. Again, derivative is like the slopes of the function. So here's further examples of what I mean. Again, this would be considered concave down. This is concave down. This is up. This is up. Um, so for this example down here, for positive slopes, this is concave up because the slope, if you were to check and actually do the calculation, you could. You don't have to for this class, but if I was to calculate the slope from down here compared to up here, you could see that the slope is indeed increasing over time. Or what if you have negative slopes? It still works in the same way. So for this one, over time means I'm going to be starting on the left of my graph. So kind of like when you're reading a book, you read from left to right. So for this one, if I was to calculate the slope of this line, I get negative 3.27. And then if I was to calculate the slope of the line down here, I get negative 0.31. Because it goes from more negative to less negative, this is going to be called slopes increasing. It's still slope increasing. It went from less negative to it went from more negative to less negative. So these both are concave up. And that just shows kind of different examples of how this is actually very true. Again, let pause if you need to ask any questions. Again, here's furthermore, if you want to test these out. Again, if these right here both are concave down, these would be examples when the slopes are decreasing over time. So if I was to find the slope of this one here, I get 2.44. If I was to find the slope of the very topmost one up here, you get 0.36. Likewise, with the negative slopes, what we're looking for is you go from more negative from less negative to more negative, because we're talking about slope decreasing. So less negative to more negative, you still get your concave down. So, and by the way, if you're playing the slides on your own computer, you should have this pop-up animation happening for yourself if you hit present, by the way. All right, let me pause to see if anyone has questions. Again, this is to further illustrate how concavity is connected to slopes, or how concavity is connected to derivatives, which again are kind of interchangeable here. Okay, so again, when I'm describing concavity, if you look back on the slides, it started off very basic, like this is concavity, here's a visual. And then I started talking about slopes, and then I kind of made a connection to derivatives. So that's all we have so far with concavity. Again, you will not be asked to calculate little slopes like how I'm looking at here or how I'm showing you here. This is just for you to understand that concept of how it's connected to slope. So don't be worried about that. Okay, and then here's an easier way to think of it. The first derivative, right? The thing we were working with before we went into break, it tells us the slope of a curve at any point. But whereas the second derivative tells us how the first derivative is changing, because the second derivative is the thing that's going to be connected to concavity actually. So you're going to see in a bit. It turns out this is the big idea down here. This is the main thing you want to take away from here. When the second derivative is negative, that means you're going to have concave down. So again, when the second derivative is negative, that's going to tell you that we have concave down. That means you're going to draw a cusp that's kind of like facing downward. And when we have a derivative that's when the second derivative is positive, that means we're going to have that at that interval or that section of the graph, we have concave up. So these two are going to be the things we'll be using. That's just from all this discussion. It comes down to these 2 points. And that's how we're going to be using the second derivative test. All right. So just to make, again, this is the original visual I showed you. And again, just to make a connection with what I just said in the last slide, remember concave up means the second derivative is positive. In textbooks, you would see it written like this. The second derivative, so f double prime of x is greater than 0. That means second derivative positive. That's how you would see it in the textbook. Same thing up here. I mean, I don't really care whether it's decreasing or increasing. To be honest, I just care whether or not it's concave up or down. Again, this is when the second derivative is positive, same thing. And when it's concave down, all that means is that your second derivative is negative. Here's the mathematical notation for being negative. Likewise, same thing over here. So that's just kind of what we kind of concluded there as we looked at the concavity, looked at the slopes, and now we have a connection to now the second derivative and how it's even related to it. And that's gonna, lead us into the second derivative test. And it's gonna really help us when we sketch our functions. All right, cool. So again, I'm mostly just pausing to see if a question comes up or anything like that. But otherwise, let's go on. I'm on slide 14. I'm going to head over to our Padlet check. So this is our pause and check. I kind of wish I did build a little bit more pause and check, but let's do this first, pause and check. Now, if you're on the slides with me, the Padlet will be right there in the notes section, but I'm going to go ahead and put it in for everyone else here in the chat. So this is where you're going to pause and participate because I do enter in these participations into our Power School. Reason for that is I don't want to just grade you on asynchronous work. I also want to grade us on in-class engagement, which a lot of us do a lot of good stuff in. All right, so once you open the Padlet, you could, by the way, you could review all these prompts we had before, but to help you refresh, we're going to be on column number 9. So I'd like you to check your understanding on concavity. You want to determine the concavity of this graph by color. So you could say the red one is, and you could say concave up or down, blue one, purple, and then there's the orange. Go ahead and take your time on this. Let's take about a minute or two and then we'll come back. Again, let me put the directions in the chat for the nonverbal learners, of which that would totally help me if I'm on the class. So All right, let's have a few more seconds. So far, it's looking pretty good. I'll see if there's any questions I need to address on there. All right, let's go ahead and come back together. Do make sure you put in your 2 cents there for your credit here today. So describing the concavity by color, most of you are pretty much on point. So a lot of you agreed. The first one there in red, concave up, and then we have that it's the graph begins with a decreasing concave up. Let's see if anyone. Let's see what else we have here though. Concave up decreasing. We have here concave up increasing. So I'm just trying to check out these increasing versus decreasing. We have concave up decreasing over here. Concave up decreasing. We have concave up increasing down here. We have the red has a decreasing concave up. So we can talk about that. To be quite honest, you all are right on the concavity part. We're not really going to focus much on the increasing or decreasing, but just because I saw a variety of different answers on whether or not the slopes are increasing or decreasing, to check this, I basically, again, I need to use my straight one. So I'm going to pretend I have a ruler and I'm going to just draw tangent lines. Oops. So it's not touching my curve. So try again. This is a tangent line. This is another one. So far it's negative and it's pretty negative steep. And then it kind of hits 0 down here and then turns positive. Oops. For the red portion. So because it's very negative, so very steep up here, and then it gets less steep. So it goes from negative to positive. Oops. Negative to positive. I would say that this is increasing. I don't know if y'all see that because this is a negative slope and it's going to positive. I would call this concave up increasing. Let me know if anyone wants to kind of debate that. But to be honest, the more important thing here is knowing whether or not it's concave up or down. We're not going to really focus on whether it's concave up increasing or concave up decreasing or whatever. But that's what I would say, my 2 cents, just because I saw different answers there for whether it was increasing or decreasing. But otherwise, y'all were spot on, y'all. So this was great. Yay, because again, that would take practice to kind of determine increase versus decrease. Again, let me know if anyone has questions about that though. Okay, let's go ahead and jump back into our slides. That was a great check. Now, some of you kind of remember, in order to kind of teach these calculus concepts, it's really great to kind of have a real world connection. So I'm back on the slides, everyone. I'm on slide number 16. So we're gonna leave the Padlet. Again, make sure you put your contribution in there. And we're gonna talk about inflection points. Why I'm talking about an inflection point is because it is strongly related to concavity, and it's also strongly related to when we talk about the second derivative test. So this is some actual data, everyone, from Verizon Wireless. So their data trends can actually be modeled by a function. And again, you use statistics. Basically, people don't really actually use Desmos to model their functions. Sometimes they use very sophisticated statistics tools, right? So they were able to model it with this here function, and they found an inflection point. Now, what is an inflection point? First off, inflection points are where concavity changes. So concave up to down or from down to up. And in business or in other fields, inflection points are events that result in significant change in the progress of a company or industry, and often details a point in which business could grow or decline. So how does that happen here in this Verizon example? So if you notice up to 2008, or right before 2009, the graph is, or the curve is concave down. It's kind of cusping downward. This would be concave down here. And if you want to think about slopes, the slopes are decreasing over time because it gets more steep to less steep. So this would be a decreasing concave down. So that's what's happening here. Then right after the inflection point, the curve becomes concave up, which means the slopes are going to be increasing over time. So this is going to be a concave up. So notice how before this, their sales or their whatever were decreasing over time. Whereas after that inflection point, we have a growth in business. So this is kind of like how it's going to relate to the real world. So that's just one example. Let me know, does anyone have questions about what is an inflection point and how it relates to the real world? All right, awesome. Let's go ahead and jump into the next line of business here. So, all right, I keep referencing the second derivative test. Well, what exactly is this? We know all about the first, hopefully. And if you don't worry, you got your big ideas packet and we have a plan for review. But what is the second derivative test? The what? So what does it tell us? The second derivative test will tell us about a function's concavity. Yes, that's the connections we're making here. So it's going to tell us whether what we say is bends downward or bends upward. That's another way you could think of concavity. It also, the second derivative test will also allow you to find inflection points. Again, these points are so important when it comes to business and determining growth and so forth. Even in the stock market, you can even use it for the stock market. But again, inflection points, if your function has them. Some functions don't have it, right? Like a line doesn't have an inflection point. It's straight up going, it's just a line. So that's the what. And how exactly do we do it? So that was the what, now we have the how. So how do we actually do the second derivative test? It's actually going to look very similar to how we do the first derivative test, except now we're going to be paying attention to when the second derivative is negative. So when the second derivative is negative, that's when your function is concave down. And let's not forget, when the second derivative is positive, that's when we know your function in that area is going to be concave up. That's how we're going to be using the second derivative test. And that means that the inflection point occurs when the second derivative is equal to 0. And the reason for that is because you're going to see that critical point for the second derivative test is going to be where that concavity changes from either up to down or down to up. So again, super important. Let me let you all read this slide. Just to let it soak in. Maybe you want to add some questions on your slide that you want to make sure you ask whenever there's questions again, or an office hours would be great too. All right. So those are the different components of the second derivative test. Okay, y'all ready for this example? So this example is telling us find all inflection points and intervals where the function is concave up or down for f of x equals x to the third minus 9x squared plus 7x. I apologize. My exponents look very huge, but that was the best I could do. I don't know what happened. All right, let's do this, y'all. So this is the second derivative test, and these are the steps. Again, it looks very familiar because it looks like the first derivative test. All right, step one, you take the derivative, right? This is very similar to the first derivative test. Step one is let's take the derivative. Bring down the 3, subtract 1, you get 3x squared. Bring down the 2, because there's a 9 right there, you got to do 2 times 9. That's minus 18. And then if you subtract 1, you just get x. And then remember, the derivative of a linear function, which is like anything that's just next to x, is just the number itself. So let me just make sure, does anyone have any questions about the first derivative before I move on? All right, and then feel free to put your questions in the chat, and I could also go back in case if I'm moving too quick. Now, what makes this different from the first derivative test is my next step here. Because this is going to be the second derivative test, we're going to take the second derivative. What that means is we need to take the derivative of the first derivative. You know what I mean? And it's kind of weird. So we're taking, to get the second derivative, you take the derivative of this. So see how the 2 comes down, 3 times 2 is 6. And then 2 minus 1 is just 1, or just, you just get x, minus the derivative of a constant, the derivative of a linear function is just going to be the number in front, so minus 18. And remember, y'all, the derivative of a constant, that's a number by itself with no variables next to it, is going to be 0. So that's why I didn't even write down plus 7. So here's the next step, and this is the second derivative test that we're doing. We have to take the second derivative in order to find inflection points and the concavity of our original function. Remember, this is our original function. Our goal is to try to kind of figure out how this function looks like using calculus. All right, let's see if no questions on the second derivative. Make sure that you understand how we got that second derivative. All right, the next step is going to be the same steps as your first derivative test. You got to set this equal to 0 because when your second derivative is equal to 0, that's where inflection points happen. So maybe you want to make yourself a little comment on that. So again, we're going to set our second derivative equal to 0. After we set this equal to 0, remember we got to solve for x. We're trying to find the critical points. So let's go ahead and solve for x. So I got to add 18 to both sides. And then in order to solve for x, divide 6 both sides. And what I got was x equals 3. Now, the reason why I kind of paused when I say critical points is because there is a slight terminology here. When it comes to the second derivative, when we solve for x, it's actually called a subcritical point. It's weird. I'm not going to be picky about it. You could still call it a critical number if you don't want to say subcritical. But formally in textbooks, they're going to call this a subcritical point when it's the second derivative test. So just a little note on why it says subcritical. So, okay, great. So we got a subcritical number or a critical number. Our next step is going to be the sign chart. So don't forget, remember how a lot of you got to this step in the first derivative test, but after you were a little bit lost. That's where we want to focus our energy though, that part that we get stuck on. So we have the critical number. Next is we got to place it on the sign chart and apply the second derivative test. First off, does anyone have any questions on slide 19 before I go on to slide 20? Okay, I'm hoping the steps are not too foreign so far. Okay, let's go on to slide 20. Now let's put this on the sign chart. So remember our subcritical number was 3. So I'm going to make my kind of like a number line. And I'm going to put 3 right smack dab in the middle. We only have one subcritical number. Yep. Great. And now comes the tests. So for the second derivative, what we're testing is concavity. We're not trying to test for maxes or mins. We're testing for concavity. So how this is going to work is you're going to choose any number to the left of 3 for the first part. And the number that I chose is 0, because 0 is a very nice number because it usually cancels things out. I want you to read the steps. And I know I tried my best to make this pop up step by step. It wouldn't let me. So here's what I'm doing. I check any point to the left of 3. And we have to plug it in. Pay attention to this. So this is a part that a lot of you got stuck on. For this step, we have to plug it into the second derivative because we're doing the second derivative test. This was our second derivative. You could look back on our slide, prior slide. This was the second derivative that we found. We need to check and test the number to the left of 3, and an easy number is 0. So all I had to do was I plugged in 0 into here, right? 0 got plugged in right into this x. And that's how I got negative 18. So again, pay attention to that step. And notice how I'm going to make this connection to concavity. Because the second derivative is negative at this point, at x equals 0, we say that the function itself is going to be concave down on this whole interval to the left of 3. So that's humongous. So this negative for the second derivative test means concave down. So let's see, does anyone have questions? It's going to be concave down. I see something in the chat. It's increasing, right? I believe so. The slope is increasing. Is that what you're asking? I don't know. I guess we'll look at the picture. You could check if it's increasing by, if you test a number more to the left of 0. But that's a good question. I guess we'll see when we check out the graph. To be honest, I can't tell at the moment whether or not. Next, right, we got to finish checking all portions around the critical number. Next, we're going to check any point to the right of 3. And the easiest point I could see that's to the right of 3 is going to be 4. That's the smallest number. So what I did is I took 4 and I plugged it into my second derivative. Again, same thing. Into my second derivative. Again, that's right here. That's the one we found in the prior slide. I had to plug in 4 because that's a number to the left of 3. Remember, any number works. I'm just trying to choose the most convenient number. And I believe I got 6. Y'all can double check my work. So 24 minus 18, 6. And now, because the second derivative is positive, we say that the function on this side of the domain, or the 3, is going to be concave up. So this plus right here is going to mean concave up. And then I do see something in the chat. Again, let me know if you all have questions. Concave down, but increasing, says it goes from negative 18 to 3. So 3 is the number. 3 is the critical number, which is not a slope. So when we're talking about increasing or decreasing, we're talking about slopes. So if you're talking about slopes, then that's right. Not sure if you're talking about the slope, like when you're saying 3. Okay. All right, y'all, before we go, let me show you how this looks like. And don't worry, we'll get to review this. But yes, it's a lot of steps, so it's okay if you feel overwhelmed. Let's look at the graph. And we could talk a little bit more tomorrow on how I knew exactly at this coordinate point was the inflection point. All we knew so far was that at 3, we had a subcritical number. And we could talk tomorrow on how I got negative 33. But this is what it looks like, guys. I just used Desmos to kind of plot the original function, but you could see how this inflection point and how we got that this was concave down and this was concave up. So it's actually like very verifiable. It's really cool. Again, let's talk about this tomorrow, and we could go ahead and pause there, y'all. Feel free to stay back if you have any questions, though. Yeah, I don't think we'll do a checkout because we're out of time, and I want y'all to enjoy your lunch. Okay, y'all, have a great lunch. I'll see y'all tomorrow. Bye, everyone. See ya. Bye.